Hello everyone, and as always, thanks for taking your time to watch this video. General relativity and special relativity have changed the way we view physics today. However, exactly what are they? First, let's answer a common question. What is the difference between special relativity and general relativity? Special relativity, published in 1905, talks about non-accelerating bodies moving at high velocities, while general relativity includes gravity. So how did these theories exactly come into play? Maxwell's equations in 1861 summarized the interaction between electricity and magnetism in four beautiful equations. And during this, scientists that were looking for the ratio between the unit of electromagnetic charge and electrostatic charge found it in Maxwell's equations. This relationship gave a velocity the same value as the speed of light, and proposed light to be a wave. However, in order for Maxwell's equations and the experiments done to be true, light has to have an absolute velocity. But that contradicts relativity, which says velocities are relative to the observers. Take this example. For observer A, a car traveling in a direction for 100 meters in 1 hour would be traveling at 100 meters per hour. But for observer B, who is in another car, moving at the same speed in the opposite direction, the car travels 200 meters in 1 hour. So the speed is 200 meters per hour. This was convoluted for light because it has to have a velocity of 2.998 times 10 to the 8th meters per second, relative to everything for electromagnetism and electricity to be related. But how can it? Our hero, Albert Einstein, provided the answer. He said that light is in fact the only absolute velocity, and all observers see it going at the same speed. This is what brings time into play and why Murph becomes older than Matthew McConaughey in Interstellar. Let us say that we have two cars. One is stationary relative to us, while the other is moving. Let's assume, when at the same point in space, both cars fire a laser. After the laser reaches a certain point, let's say here, for the sake of simplicity, let's say both lights have moved about 300 million meters in one absolute second, so the speed is 300 million meters per second. However, light B has only moved 100 million meters in 1 second relative to our super fast fictional car. So its speed is 150 million meters per second. But we know that it has to be 300 million meters per second because light has to be absolute. So how can that be? Let us further break down the velocity formula. Change in displacement divided by change in time. If displacement has to stay the same, but we need the velocity of light to go from 150 million meters per second to 300 million meters per second, we will have to decrease t to 0.5. This way, light B is still moving at light speed relative to everything, including car B. However, for every second that passes by, for car B, only half a second has passed by. This seems to be counterintuitive because we do not see it occurring in everyday life. But remember, cars don't travel at 150 million meters per second in everyday life. The distance traveled by the observers are very small, so time only has to change a very, very, very minute amount for it to have any kind of effect. This is called time dilation. The second part of special relativity says that the laws of physics act the same at constant velocity, which makes sense, because if Einstein is moving and he throws a ball, him and the ball were already moving at the same velocity. So it is as if they are not moving at all relative to them, because if he looks at the ball, it's not moving, and the surroundings don't affect anything. It's just that relative to the surroundings, him and the ball are moving faster. Note that F equals ma, not F equals mv. So velocity does not matter. It is just the change in the velocity that does. You cannot tell if you are moving if you are on the Earth, which is in fact rotating, and the Earth is orbiting the Sun. So you are moving at 30,460 meters per second. Furthermore, the Milky Way galaxy is moving, and the universe is expanding. So you're actually moving really, really, really fast. But you just can't feel it. However, you can feel acceleration. A car can brake, and you will feel it. This connects back to us saying that light is relative to everything, because light is a defined quantity in Maxwell's equations. And for the laws of physics, including Maxwell's equations, to work in every frame of reference, then light has to stay the same in every frame of reference. Then, to the next fun part. General relativity. General relativity says that space and time are interlocked, which makes sense in terms of special relativity, because time is not absolute just like space and can vary for different observers. General relativity gives a new way for physicists to look at gravity, and is a new explanation for it. Another way of looking at space-time is space being the video and time being the sound of a movie. You cannot see the sound, but it still exists and it's still affecting everything. But what exactly is space-time? Space-time is what refers to the external reality that underlies our collective experiences of the space between things and the time between certain events. Why is space-time necessary? For example, let's say there are two trees and observer A is standing in the middle of those two trees just a bit further away, and observer B is standing closer to one of the trees than the other. Now let's say lightning simultaneously strikes both trees. The light from the strikes approaches observer A at the same time, so for him, both got struck at the same time. However, for observer B, the light from one tree came faster than that of the other. So he says that that tree got struck first. So who is right? It turns out they both are not wrong. The time for events and the space between events might be different, but all observers will agree on the space-time interval. So the space-time intervals are the only objective measurements. This means that the only things that are real and objective are the relationships between events. Now, let's talk about how gravity is illusional and relates to all of this. Let's say Einstein is standing on the back of a truck, and the frame of reference is on the truck, which is accelerating forward. It will look like he is accelerating backward. So, when an apple is falling down, is the Earth actually accelerating up? And this can be true because of the equivalence principle, which is the inability to distinguish between free fall and lack of gravity. However, since the Earth is curved, if objects are falling, then they move toward each other, accelerating. For this to be true, space-time has to exist, and it has to be curved. Since objects that are turning also accelerate, if we can make objects on a curve move at a constant velocity, then inertial frames of reference can be free-falling objects. And straight lines on a sphere are straight, even though it is curved. Watch this piece of paper. The line is obviously straight. If I roll the paper or bend it, the line looks bent, even though it is straight and I did not alter it. Even if two lines are parallel on a sphere, they will eventually converge and then diverge, even though they are straight. Geodesics. These are the lines on a curve that are straight but appear to be curved. Now, let's assume a light beam is coming at the Earth. As it approaches Earth, it experiences the space-time curvature around the Earth and travels on a straight line geodesic. Remember, it is still traveling straight, just on a curve. Gravity does not make them travel curved. It just changes the way they travel straight. This can explain why bodies orbit other bodies. Now, if the disturbance caused by an object is not so great, then the other object can escape its curvature. However, if the disturbance caused by an object is so great, for example, a black hole, then the other object cannot escape its curvature. This explains why not even light can escape a black hole, and it might lead to learning about different dimensions and how they are connected. What if the disturbance caused by gravity in a black hole is so great that it disturbs and leads into another dimension? Again, thank you so much for watching this video. It truly means a lot.